Okay, so we're going to do two problems out of 12.6. The first one, so the directions say, show that the ratio test is inconclusive, and then apply tests from earlier chapters to determine the convergence or divergence of the series. And so you have here the sum from 1 to infinity of -1 to the n, and then natural log of n over n, right? And so the first thing they're telling you is show that the ratio test fails, right? And so let's do that real quickly, but I don't tend to ask that as an actual question. But I'll just point out one more time, right? There's no exponential, there's no factorial. Most likely the ratio test is going to fail. So there's the n plus 1th term, and then what do we multiply that by?
N over log n.
Yeah, and I'll put the -1 down here too, right? Again, the negative ones are just gonna disappear because of the absolute value, right? So this whole thing will turn into this, and now, again, I'm gonna put the logs together and the other parts together, right? So I'm just gonna take, when I multiply this, I'll just switch the numerators. Does that make sense?
Yeah.
So I'm just gonna write it as n over n plus 1 times log of n plus 1 over log of n. Is that okay? All right, what does n over n plus 1 do as n goes to infinity?
1.
Goes to 1. So this thing's gonna go to, I'll write it out this way. Right, your log rule, or your limit rules tell you you can split up limits as long as they both exist. So you can save time if you feel comfortable with some of this, but worst case scenario, you do this. That limit's 1, right? And then what's this limit? Well, it's infinity over infinity, right? It's going to be 1 as well, but you should show your work. So if it's infinity over infinity, you can use L'Hopital's rule, right? So limit as n goes to infinity of 1 over n plus 1 over 1 over n. And that's 1, or you can flip it over again, right? We're back to that same thing. That limit's 1. And so the ratio test. Does that make sense? Now it says, determine if this converges or diverges. On the next test, you might see determine if it's conditionally convergent, absolutely convergent, or not. And this one turns out to be conditionally convergent. It's actually bigger than the one we did earlier, right? The 1 over n log n. That's bigger than it. You've moved a log n up top. So you can show that's conditionally convergent, but all we care about here is convergent or divergent. And so we're going to use the alternating series test again. So we just write out b sub n log n over n. So what's this limit? I guess I didn't really even need to call it b sub n, but that limit is
1.
no.
Because
Yeah, right. Logs grow slower than the other thing, but if you have to, you do L'Hopital's rule again, right? So infinity over infinity, 1 over n over 1. You get a limit of 0, right? So we're going to use the alternating series test. That's the first thing. What else do we need to show?
It's decreasing?
That it's decreasing, right? So the alternating series test requires the b sub n's are limit is 0 and they're decreasing. And so just for, if you want to do it with n's, I'm not going to argue with you. But you really can't differentiate a sequence, right? You can differentiate a function. So you should, in reality, switch over to this, or at least understand that if you take your derivative, you're doing this. So that one, I'll say, again, right, it's an infinity over infinity, so it's not as obvious that it's decreasing. You're not just dividing by bigger and bigger stuff. You got the numerators getting bigger, the denominators getting bigger, and so you should show additional work in this case. So what's your quotient rule? 1 over x times x, right? Minus x times, log x times the derivative of x, and then all over x squared, right? So So you get this, so that's 1 minus log of x over x squared. So is that thing negative?
Yes.
Always?
no,
No, when?
when x less than one, larger than zero.
Right, so you need, the denominator is always going to be negative, right? And so let me just say, if we set that equal to 0, we get what? Log of x equals 1, so what's x?
1, 0,
No.
1 over,
Oh,
Right.
yeah.
So it's e. That makes sense? So that's the point. And again, you don't have to exactly find this. All you have to say is, I know that goes to infinity, right? And so 1 minus that is going to eventually be negative. But you can just say this. So for x greater than, well, greater than e. Does that make sense? So again, limit 0, it eventually decreases, and so you can apply the alternating series test. So by the alternating series test, okay, that makes sense? And then 17, or no, 23, I think it was just use the ratio test, if I'm right. 3. Right, so what was it? It's n squared over e to the n. Okay, so just use the ratio test. Right, again, exponential, right? So you know that ratio test will probably be useful. Right, plug in n plus 1, you get that, times e to the n over n squared. This time I'm not even bothering with the absolute value because everything's positive. Same, so you can clean some things up from there, or I'll just write it like this. This is n plus 1 squared, right, over n squared, and then e to the n over e to the n plus 1. Just rearranging things. What happens with the e's here?
cancel, so there's just
One, so they
One.
cancel, there's one e and it's where?
Um,
In the denominator, right? So you get this, and it cancels out the exponent, but you still have a single e down there. And what does n plus 1 squared over n squared go to? 1. So this whole thing should go to 1 over e. Right? And e is greater than 1, so 1 over e is less than 1. So what's our conclusion?
Absolutely.
Yeah. So therefore, this converges by the ratio test. And again, the conclusion is really, or from the statement is that it's absolutely convergent, but that's stronger, right? So if it's absolutely convergent, it's convergent. And in this case, everything's positive, so absolute and convergence just are the same. Is that okay? All right. Any other questions from 12.6 then? Okay, well, we'll stop there then.